Hello, welcome to the course Electronic System Design. Last few lectures we are talking about a digital implementation of a function, and we want to create a complete system by implementing all these functions. So now we have so many functions which we want to integrate on a single system or a single chip, and the question is how can we do that. So one function is, for example, there is a function which is having, let us say, 5 input variables a, b, c, d, e. So this function is nothing but the logical AND or combination of all these variables a, b, c plus a, b bar, c plus b, c bar, and so on. So this kind of function we want to implement using some digital circuits such as NAND gate and NOR gate. If we talk about limited set of inputs, for example 5 inputs or 6 inputs, it is easy to do that using some techniques such as K-map. We can optimize this, or we can use Boolean algebra to optimize it, and we can implement using NAND and NOR gates. However, if we want to talk about a bigger system, for example a complete processor or a very complicated IC which performs so many functions altogether, that time it's not possible to do it by hand or using some techniques on the pen and paper. So that time we need some kind of softwares to optimize them properly and make and implement those digital circuits. So that time we need some particular softwares which can understand what a variable is and how the output variable is dependent on the input variable and what is the expected output for a given set of inputs. So that time when we define a system, when we first want to implement a complete system, that time we do not know the internal architecture of the system, we know the behavioral architecture of the system. For example, we have, let us say, 5 switches in the room, and one switch should turn on the fan, one switch should turn on the light, one switch should turn on the heater, and so on. So that time we do not know the actual circuit what we are going to implement inside those switches, but we want the behavioral specification at first place. So when the system we want to start making, that time all the specifications are behavioral in nature. We do not know the exact circuit behind. So these behavioral specifications we need to take into the implementation phase, or that is called the synthesis, when we want to synthesize our design, this behavioral code. So that time we need particular set of softwares, and the Boolean algebra, which is the key algebra to optimize all these functions, that need to be taken care by the tool. This is how we can handle the large complex designs, because if we have, let us say, more than 10 or 20 input parameters, it is very difficult to make a single truth table for all these functions, because the number of rows in the truth table is 2 to the power n, where n is the number of variables. So for a variables of, let us say, 5, the rows will be 32. However, if we just increase one more variable from 5 to 6, the number of rows becomes 32 to 64. So the complexity of the system going exponentially with the input variables. So the input variables we need to be having the very limited set. So when we do that, when we design a complete system, this is also possible that the output, for example, we have, let us say, n inputs and we have m output. So the first output need not to be necessarily depending on all the n inputs. It is depending maybe only on the first 3 inputs. So that time when we cross check, we need not to apply all the possible combinations on n variables, because the output 1 which we are currently checking the functionality, this depends only on the first 3 inputs. So, that time if we have the knowledge of system design, whatever is inside that system, it helps reducing the complexity of the design system. So, these large number of inputs and outputs, that is handled primarily using some softwares. And can we use SPICE to do that? The answer is not practical to use SPICE for all these simulations, because remember, the SPICE is solving the physics based equations for a single MOSFET. So, if we have a gate, for example, NAND gate which use 4 transistors, 2 PMOS and 2 NMOS, for a single transistor, for a single NMOS, SPICE is solving more than 100 equations to get the desired output. So, for a NAND gate, it is solving 4 times the equations. If we talk about n inputs, which is having, let us say, hundreds of gates, it is not possible to simulate the entire system using SPICE, though that will be very accurate output, very close to silicon, but the time complexity of that calculation will be very high. So, we cannot use SPICE simulator for this type of digital implementation. We have specific set of softwares to handle only the digital logic design. So, today we are going to talk about all those softwares which can handle these digital designs, and what are the languages which is used to design these systems. So, let us do this. So, for the background, as we have discussed, the system specifications are behavioral in nature. Handling of large complex designs is possible through CAD softwares. CAD is nothing but computer aided design. We cannot use SPICE for simulating all these digital circuits, or it is impractical to use SPICE. For simulating digital circuits. Specifically large digital circuits. This happens due to the time complexity. and we have so many equations to optimize. So manual optimization of design in Boolean equations is not possible. So we need some CAD softwares. So these are some of the problems where we need dedicated softwares to implement these digital logic functions. We have the time complexity in the SPICE software. Those SPICE software can also handle these digital logic circuits. For example, if we want to simulate a simple NAND gate or a NOR gate, then SPICE is the simulator which we want to prefer, because only 3-4 transistors we can easily implement, and the result of this NAND gate, the transition from low to high and how to low, that will be very much accurate, very close to the actual silicon. When we fabricate this on the silicon, that output will be, simulated output will be very much similar to the fabricated circuit. However, for a large number of transistors, large number of gates, SPICE is impractical. It will take too much of time and too much of memory requirements, so that it is not practical to use it. For a simple like uh, 10,000 gates, it may take even days to simulate. So that is why we need some CAD softwares. So there are multiple CAD softwares available by various industries. For example, CAD and Synopsys. These are the companies which are pioneering the CAD development in the VLSI design. They have various tools available to simulate these RTL level design or the circuit design. They have so many tools available. So today we are going to talk about the tools, or in general we can use some tools to design these digital system. To design these digital system, we use languages. We generally do not work in terms of the GUI, or we don't want to pick and place each and every gate, because now we are talking about in the millions of gates to develop a complete system. So millions of gates we cannot connect together using hands, or you cannot connect them on a computer screen by accurately. So that we do by using certain codings or some programming skills. So we have two types of programming which are very widely used in VLSI technology. One is the VHDL and the second one is the Verilog. So VHDL is actually the short form of VHSIC, hardware description language. VHSIC is again short form of very high speed integrated circuits, and then hardware description language. So VHDL is one language which is used for designing all these digital gates. The second language is Verilog, which is also very much popular for designing these digital gates. So let's see what VHDL and Verilog, what is the difference and what is their common features. वो नहीं आ रहा है यहाँ पे, वो होता है नहीं ना, दोबारा से कर दीजिए। हाँ, So the first language is Verilog, and the second language we are talking about is VHDL. So both are hardware description language. It means we can design our digital circuits and their hardware implementation using both of these languages, though still there are certain difference between these two languages. So the Verilog, this has a very good acceptance in ASIC design, and particularly the low level design, the RTL and below. So has very good acceptance in ASIC. Good for low level designs. Particularly RTL and below. This has very fast simulation speed. This is relatively simple. And this is very similar to C language. This language is mostly in North America and Asia, Japan. This is very popular in North America, Asia, and Japan. So this is the Verilog language. However, VHDL, this is relatively weaker in low level design. But this is superior in high-end system level design. This has little slower simulation time. This is relatively complex. This language is popular especially in Europe. So these are some of the key difference between Verilog and VHDL. These both are HDLs or the hardware description languages. Both are used to implement the digital logic functions. However, Verilog has very good acceptance in ASICs and very good for low level designs. We have a small system to make, then we will prefer Verilog over the VHDL. VHDL is relatively weak for small systems, but it can handle very large systems. So, if we want to go for a very big design or the complete processor kind of design, then VHDL is the preferred language for the big systems. For smaller systems, Verilog is the preferred one. Verilog has a very fast simulation time compared to the VHDL, which is little slower than Verilog. Verilog then is very simple to understand. If we know the C language, we have worked in the C language, the workflow and syntaxes are very similar to the C language. So, for a C programmer, it is very easy to understand the Verilog based designs or Verilog coding. However, VHDL is little complex than the Verilog. Verilog is very much used in industries and North America, Asia and Japan. VHDL has some limited places where it is used. This is used in academia or in Europe. So, Verilog generally is used for smaller design. Smaller is not that small. We still have like more than 10,000 gates and quite decent system size. So, in this course we will particularly discuss the Verilog language for our RTL designs. Let us discuss the design approach of RTL level designs. So, we will follow a top down design approach. So, as we discussed, we start with the system level specifications. So, the very first step we do is to define the specifications So, this is the first step where we specify the system in terms of its behavior. Then we go for high level design. We go for the low level design. And after this we go to the step of RTL coding or the register transfer logic level coding. At this step, once we do the coding, then we do the verification so that we know that whatever we have implemented is working as per our desired results. So we do the functional verification. Once we are happy with the output versus input characteristic, then we go for the logic synthesis. This is the step when we put all the gates together and interconnect them to implement the desired RTL coding and the specification of the system. If we are happy with this stage, we proceed. If we encounter some difference, then we go again for the gate level simulations. This is an iterative process at this point where we do this gate level simulations. And we go back to this RTL coding to encounter any change, or even this is sometime connected to verification as well. We do verification as well when we do all these simulations, and once we are okay with the design whatever we have synthesis, then we go for the next step, which are place and route. We physically place the gates on the layout and we perform place and route. And after we go for the fabrication. And after fabrication we do post silicon validation, which is checking the silicon for the known set of input and generating the output on the silicon itself. So this is called post silicon validation. So this is the top down design approach where we start with the system specifications. We go for the coding of high level coding, then we go for the low level coding, then RTL design. At that RTL design, we do Verilog based coding or VHDL based coding to implement the desired function. Once we implement the function, then we know whether we have implemented it correctly or not. So that we know using functional verification, where we apply certain known inputs and generate the output and check whether the generated output is correct or not. That is functional verification. If we are happy with the verification that everything is running fine, then we go for the logic synthesis. Synthesis is something, we have this Verilog code and we implement this code using the available gates we have. For example, we have NAND gate, inverter and NOR gate only. So using only these three gates, how can we implement our entire code of Verilog? So that step is called the synthesis. So once we do the synthesis, then we can go for place and route. We have this synthesized design, we put that on the actual 2D plane, all the gates together and connect them. That is called place and route. We place the gates, and route means we connect the individual terminals whatever is desired by this synthesis step. After place and route, we go for the fabrication, and after fabrication, once we get the silicon, we perform the exact same input pattern we apply on the silicon and get the output and match whether this is our desired system. So, this is the top down design approach for a digital system. Of course, there are many steps which I am not showing here. These are just the block level steps which we take to implement a complete system. Now, let us see how the Verilog language actually look like while we implement these RTL coding or the Verilog code to implement digital system. So, in Verilog, the very first thing we do is the definition of a module. So, in Verilog, when we design a system or a subsystem, that we design using the keywords module. So, when we start a module, the Verilog knows that we are going to start creating a entity in the language. So, when we, for example, write the module code, so we first start by writing module, and the simulator understand this keyword module. This keyword we cannot use it for any other purpose. These are reserved keywords of the system or the softwares. So, module, whenever we write module, system expects that we will write now a module name. This can be AND gate or OR gate or NOR gate, whatever we want to name it. We write module name, and then we write the port list. So, this port list is nothing but the set of input and output pins which this module name entity has. For example, if we talk about a NAND gate, 2 input NAND gate, then we will write module, then NAND underscore 1 or underscore 2, whatever. We can implement more than one NAND gate. So, module, then NAND underscore 1, and in the bracket we will have 3 pins, 2 as a input, A and B, and the third one which is out, which is a output. So, we will write A comma B comma out. So, that will be the port list for that NAND module. So, when we write this port list, we have to declare to Verilog whether this is of input type or output type. So, first when we write this port list, we have to immediately declare them that port is input port or output port. So, we need to have port declaration. For example, pin A is the input pin. So, input A, input B, and output space out. So, that is the something called port declaration. Then we can have some directives which we can include. These are additional directives we want to include in the simulation to tell Verilog about some desired functionality. Then we have variable declarations. We use so many variables inside the module. We will have various assignments where we will assign the value to a variable using some input parameters from A and B. So we have assignments statements. We can even call a lower level module also in this module. For example, if we are making a complete ALU here, this so module will be ALU, and in ALU we can use NAND or NOR gates, so we can call them here. That is called the lower level module instantiation. We can have initial and always blocks. About these things we will discuss later in another lectures, how the Verilog code actually look like. Today we are just discussing what the Verilog language is and what are the syntax. So initial and always blocks we can have. We have various tasks and functions as well. So these are the various things we have in a complete module's body, and when we have this complete block is called the body of module. And once we are done with all the specification, we can close down this module by the keyword end module. So when we write end module, we are actually closing down this first module from where we have started. So from this module to end module, this is one instance of a system. This can be AND gate, OR gate, NOR gate. You can specify the name using module underscore name. So we have all these three, these different segments of the code, and comments in the Verilog we can write using certain characters. For example, if we want to put comments in Verilog which we write only for our understanding, we do not want Verilog to simulate them. So if we want to have a one line comment, we can start anywhere by typing these two slashes. So this will be a one line comment. Now you can write after this, you can write anything, and Verilog will not treat this as a part of code. If we want to have more than one line as comment, for example, you want to write specification and some clarification about those specification, that time we can use block comments. This you can start by slash star, and then you can write anything, and whenever you want to close these comments you write it like star and slash. So anything in between these two patterns will be treated as comments. Whatever is written here, that will not be considered in the Verilog coding. So this is how a Verilog code look like. This is the basic structure of Verilog code, where you have module name, where you want to specify that this is my NAND gate, and again based on the technology or based on the delays, based on various different factors. For example, NAND gate, I have 2 input NAND gate, 3 input NAND gate, 5 input NAND gate. So I can instantiate by using different modules. So module NAND underscore 1 can be a NAND underscore 2 can be a 2 input NAND gate, NAND underscore 3 can be a 3 input NAND gate, and then accordingly I can specify the port list. A, B, C are the inputs and output is the output port. Then we have functional declaration. We have defined variables which we will use inside the block to solve certain equations. Assignments, lower level modules, we can call a lower level module in this module. For example, we are making a bigger system which is using 10 smaller systems like AND gate, NOR gate, so small ALU, multipliers, adders. So those lower level modules we can instantiate in our bigger module using this body segment. We do initial and always block, and task and functions we can include. Whenever we want to close it, we write end module. So Verilog knows that from module to end module, this is one block made up for one entity, which is named as module underscore name. We write comment. We have to write comments for the clarity of our code. So if it's just one line code, we use 2 slashes and write anything after that. If we want block comments, let's say in the starting of the code we want to write all the author's information and what is this code is all about, what is the entity, what it does. So in that case we want to have block comments where we start with slash star. Anything we write after that is a comment, and then we close the comment by star and slash. So this is how a Verilog code typically look like. In some later lectures we will see how to write these Verilog codes. So today we are going to discuss only how the Verilog actually works. So this is basic structure of code. Now when we say we want to implement a logic function, we can implement it using 3 different ways. So the very first one is the structural level implementation or the coding style. When we write a Verilog code, we can typically write the Verilog code in 3 different types, and these are different than each other. So let's first discuss what is the first type of coding style, which is the structural level coding style. So we have structural coding style. In this type of coding style, let's say we have these are our inputs and this is our output, and we exactly know how the inputs are actually creating the output. For example, here this input 0 and select input 0, these are connected to this gate which is a AND gate, and select 0 is applied to this inverter, and this signal comes to here, this in 0 signal comes here, and this signal cell 1 after inverter this comes here, this is the AND gate which is generating Y0, and then all these Y0, Y1, Y2, Y3, they go to a OR gate and generate the output signal. In this kind of coding style, we know exactly the system inside this coding, and we write the code in such a way that input 0 goes to a AND gate, and then the output goes to a OR gate and then creates the output. So the circuit is actually specified in terms of instantiations of lower level components. So these are the lower level components. Such as NAND gate, NOR gate, OR gate, whatever is available to us from the other team, or we have already designed these NAND NOR gate in our library. Now we are making a complete system and we know the structure. So this is called the structural level coding style. So here the circuit is specified in terms of low level components. These can be NAND, NOR, etc. These are connected with internal signals. For this type of circuit, actually synthesis is very straightforward. So one coding style for this type of circuit, it look like this. For example, we have a module which is a MUX 4 to 1. This is the pin list where we have one output pin, which is this thing, and then we have input pins, input 0 in 1, in 2, in 3, select 0, select 1, which are these input ports. Then we use the wires inside, and inside this we use different modules. For example, this is a NOT, which is this inverter, this is a AND gate, this is a OR gate, which we are using from our own library. So because we know in this circuit all the things, all the AND NOR gates, whatever we have, this is already there in our library. We are writing the code so that we know the actual functionality. For example, output of AND goes to the input of OR. We know all this information, so the synthesis or putting them in place, making a realizable circuit is easy in terms of structural level coding style, where we have written this code in the structural coding style. This is very easy to synthesize. However, for a very big system, it's not easy to know all the structural level coding. For example, we have 1,000,000 gates, then we cannot know which input comes from which output of the particular gate among these 1,000,000 gates. So structural level design coding is very easy to synthesize, but it needs lot of information about the functionality of the system. So, this is the first one, coding style. Let us go to the second one, which is a data flow type of coding style. In this type of coding style, we have the system definition, we have input pins and the output pins, and the input and output are connected through logical operations, where for example we have written logical AND. So, we want to do a logical AND between this input and this input, and want to provide this output which goes to the input of a logical OR and generate output. Here the difference between the first structural is, in the structural we already knew the module, we have already designed that module AND gate in our library. However, here we are just writing it in terms of some assignments. So, we are just mathematically expressing that a logical AND should be there in between these three inputs. This is data flow kind of coding style. So, in data flow coding style, it is similar to logical equations. This is composed of expressions made up of input signals and assigned to output. So, the expressions are assigned output. So, this can also be translated into structure. So, synthesis is okay. You can synthesize it using some known logic AND and OR gates, and the code in the data flow coding style looks something like this. We have the same module mux, which is 4 to 1. In this is the port list. However, instead of calling the NAND and NOR gate from the other library, we just assign the output, which is this output pin. This is OR function. OR is implemented by this straight line. So, this is nothing but OR of 4 signals. One is, let us say, this signal, which is, let us say, 1. This is 1 is from here. This is 2, this is 3, this is 4, and on from these 4 signals we are taking a logical OR, which is represented by this line, and inside this is assigned using the input variables, which is selector 1, selector 0, input 0, and so on. So, this is how we are assigning the output from these inputs, because here also we know we are implementing a AND or implementing a OR. So, it is easy for the Verilog to pick up a standard AND gate or standard OR gate and put it in this equation to implement this function. So, synthesis is still okay in the data flow statement. Now, the third type of coding style is behavioral. In this type of coding style, we just know the output pattern with respect to the input pattern. So, for example, if input comes 0 0 0 1, the output should be 0, and when the input pattern comes 1 0 1 1, for example, then the output should become 1. So, this kind of behavioral connections between output and input is the only known thing, and we do not know any circuit or any connection inside the module. So, that type of coding style is called the behavioral type of coding style. So, here we specify the circuit in terms of its expected behavior. This is very closest to the natural language description. For example, if we want to verbally specify the specification of a module, this is how we do it, that output should become 1 for this, and output should become 0 for this. So, this is how we actually define in the natural language. So, this coding style is very much close to the natural language description. This is most difficult to synthesize. This is a particular behavioral coding style. We again start with the module definition of mux 4 to 1, and here we have this always statement. This is nothing but we are defining the functionality always at selector 1 or selector 0 or input or any of the signal comes in, then we begin the case selector 1 and selector 0. Based on selector inputs selector 1 and 0, the output is either this or this or this or this, and by default the output should be 1 bit. So, this we do using begin and end statement, and this is the end module. So, here we have behavioral type of statement where we define a system using our natural language or very close to the natural language. We do not know the system, what is the structure inside the code or in the system. We only know the output pattern for the input pattern, and we write the code in such a way that output is this when input is this. So, this is how we write behavioral code. However, in this case Verilog does not know whether it should connect a AND array of AND gate, array of OR gate, or the inverters, and how it should connect it to implement this type of functionality, because the inside functionality we do not know, and for the Verilog to deduce that functionality or deduce that structure from this Verilog code is very difficult. So, this type of coding style, however, it is easy to implement, but these are very difficult to synthesize. Synthesize means using only particular gates to implement the complete circuit. So, we cannot implement this whole circuit with AND and OR gate if we do not know the connections, how to connect this AND and OR together to implement the desired functionality. So, behavioral type of coding style easy to implement, but it is very difficult to synthesize. So, these are the 3 different types of coding styles we use in Verilog based hardware design. So, this is all for today. Thank you.